This is going to be part 5 of the limit videos, so limits, part 5, and we're going to be going over vertical asymptotes. So vertical asymptotes. Before we do the definition, let's go over what it looks like. So let's say I have this graph here. And I have this squiggly line right here that is going to positive infinity on one end and negative infinity on the other side here. Well, this is what we call a vertical asymptote. Anytime something goes to positive or negative infinity, it's a vertical asymptote. So we'll put that as positive infinity and negative infinity. So the closer this line gets to this x value right here, we'll just call it a, the higher this number gets, and it will never actually reach this x value of a. Now it could do anything over here, it could be doing this on this side of the line. We don't really know, but that's not something we care about too much right now. All we need to know is it can't ever get to a, and it can't get to x equals b here. So it'll just keep going to positive infinity on this side or negative infinity on this side. That is an example of a vertical asymptote. Let's do the definition of it. Do that in orange. Definition. We'll say y equals f of x is a vertical asymptote if at x equals a, any of the following hold. So the first one is, we'll say, as x approaches a from the right, f of x equals infinity. And that's exactly what this is right here. Say we have x right here, and it's going towards a from the right. It's getting closer and closer to infinity. We could say, as x approaches a from the left, f of x equals infinity, and that is not represented on this graph. We could say, as x approaches a from the right, f of x equals negative infinity, which is also not represented on this graph. Or as x approaches a from the left, f of x equals negative infinity, which that's represented right here. Say we have x right here, it's to the left of this letter. B is representative of a here. I know it gets kind of confusing until you're more used to that notation. But x here is getting closer to b, but it's also getting closer to negative infinity. Or, alternatively, as x approaches a from the left or right, f of x equals plus or minus infinity. Some instructors won't like this notation. I'm not sure if you're actually supposed to put a plus or minus here next to the a, but it's something that I do, because it makes sense to most people. So let's go over some examples of this. Example 1 of a vertical asymptote. Let's say we have f of x equals 1 over x minus 4. Well, you can put that in your graphing calculator and graph it. Whenever you do graph it, you should get a graph that looks something along the lines of this. Let me do this. I'll do it in a slightly different color green. We'll have the vertical asymptote at 4, because if you notice, we can't graph this function at x equals 4, because that would give us 0 in the denominator. And the graph we get will be something along the lines of this. and my drawing is not perfect. So here, these lines will never meet. This will always be on the positive x-axis, and this will get closer and closer to this x equals 4 line without ever actually making it there. Then we have one other part of this, is right here. So this x negative line right here, this part of it, will get closer and closer to the point of origin here. Not the point of origin, the y equals 0 place. It'll get closer and closer to here without actually touching. And this one right here will get closer and closer to x equals 4 without ever actually touching it. So this is a vertical asymptote. And we write it down, the notation of it. We say that the limit as x approaches 4 from the right of 1 over x minus 4 equals infinity. So if we had an x right here, and it was getting closer and closer to 4, and it started out on the right, it would get closer and closer to infinity. Also, the limit as x approaches 4 from the left of 1 over x minus 4 equals negative infinity. That means that if we have an x that starts out right here, so it's to the left of 4, and we get closer and closer to the 4, it gets closer and closer to negative infinity. Let's do another example. Say example 2. Let's say we have f of x equals 1 divided by x squared. And we want to find the limit of that. First thing we have to do is graph it. So let's make a graph here. And my drawings are not perfect. And that graph would look something like this. Now, whenever you're seeing this, these two lines should be mirror images of each other, and it should be very smooth throughout here. So I'm a little squiggly there, ignore that. Well, the limit of this, we can see as x gets closer and closer to 0 from the right, it's approaching positive infinity. And as it's getting closer and closer to 0 from the left, it's also approaching positive infinity. Now, there's no asymptote in this graph where it's getting closer to negative infinity, because it's getting closer and closer to y equals 0, which that is also an asymptote, but it's not something we're going to be doing quite at this point. We'll probably go over horizontal asymptotes at a later time. So we write the mathematical limit of this by limit as x approaches 0 from the right, 1 over x squared equals positive infinity. And we do the same thing for the left. So limit as x approaches 0 from the left of 1 over x squared also equals positive infinity. This last example is going to be a little bit harder. Let's do it in teal. So, example 3. Say we have f of x equals 1 over tangent of x. Well, the graph of this is... Probably should have had this drawn out ahead of time, but oh well. Let's see, we'll have that there. We need pi over 2, pi, 3 pi over 2, that's a little farther, and 2 pi. And let's just show negative pi over 2 and negative pi for good measure. So you can put this in a graphing calculator. Some actually may mess this one up, I'm not quite sure. And you should get a graph that looks something along the lines of this. So this has an asymptote here, has asymptotes here, But then once it gets to negative infinity here, it actually restarts with the same thing over here. And it keeps repeating this pattern on and on and on. And it's doing the same pattern in the negative side as in the positive side. So it just goes on doing that forever. And the way we would write this asymptote is, because we have an infinite number of negative asymptotes and an infinite number of positive asymptotes. The positive asymptotes are approaching from, what I said that could get kind of confusing. We have an infinite number of x approaching a from the right going to positive infinity, and an infinite number of x approaching a from the left going to negative infinity. So we have to figure out a way to write that. And we write kind of a little formula for it. So for the x approaching a from the right, we would write the limit as x approaches n pi from the right of 1 over tangent x equals infinity. So that means, let's say we have a x right, let's do that in white. No, that wouldn't show up well. Let's do that in red. Let's say we have an x right here, and it's going to approach this a value from the right. It's getting closer and closer to here, and it's going to positive infinity. And we can also do that if x approaches a from the left. So limit as x approaches n pi from the left of 1 over tangent x equals negative infinity. Circle that so it's easier to see. So this means that, let's say we have some x value right here, and it's going to this a value right here. From the left of it, well, it's getting closer and closer to negative infinity. Oh, and one more thing we do need to write is, after this, you would say let n be an element of z, which we can worry more about what exactly that means later on. But that just means n equals negative, anything in this set of numbers, -2, -1, 0, 1, 2. So anything that follows this pattern, where we just did an ellipses for anything to the left of -2 and to the right of 2. So it's any positive and any negative integer, and the number is 0. So if n is any of those, this right here will hold true.